related to your cross section that people using Beer's law. We'll come back to talk a little bit about it. It's a rather simple technique, but if you measure I, this absorption, you would have something that look like this. This represents the absorption intensity. You will see a very sharp peak as you hit something that emit electron. This is known as, so the absorption usually go down like this, and then at a certain bit you will have a little peak like this. And here what I show is just one of these absorption edge, so-called absorption edge. And this absorption edge, of course, is very useful because this absorption edge contains electronic structure information, because here, when you hit the material just right, the material absorbs the photon and excite an electron, to upper state, and this is why you see a bump like this. Just like, exactly like your UV absorption spectroscopy, you see peak correspond to excitation, electronic excitation of the material. And what people discover is that if you look very closely on this little absorption edge, there's a little wave phenomena, little wiggles, very close to this absorption edge. They go around like this. And after about 30, 40 years of development on this diffraction-like technique, they discovered that these wiggles, the spacing between these wiggles, can actually be used to reflect what is actually taking place, what is the diffraction within the absorbing atom. Okay, so here you have a little diagram. I hope people can see this. So this is the atom that absorbed the photon, the blue one. And what happened is that the atom would emit, because if you have high enough photon energy, you would ionize, you would emit some of these electrons, ionize the atom, and the emitted electron would then come out in a spherical wave type format. So this little circle are meant to give you the idea of a spherical wave emanating from the absorbing atom. And when this spherical wave, electron wave, hit one of the neighboring atom, is starting to bounce back, right? So it's sort of like water. You throw a rock into a pond, the pond waves scattering out, and if the pond hit a marble or something, you would have secondary wave phenomena. So it's not like emanating back. So this backscatter electron wave actually affect, what they found is that actually these backscatter electron wave actually affect your absorption, your X-ray absorption of this photon, of this material. And that leads to this wiggle that you see. And this is called extended X-ray absorption fine structure. So FS stands for fine structure. So one of our colleagues, inorganic nano colleague, Eric Bose, was teaching a course, I think last term, on XAP, precisely that. Precisely using this as a material, as an X-ray absorption technique to examine different type of material, both bulk and surface-related material. Okay, so that's basically how it works. So it makes use of diffraction of outgoing photoelectron waves and backscattering effect of this photoelectron wave into the absorbing atoms, and then this affects the absorption edge of the atom. And by analyzing the fine structure, you would get interesting information. I actually worked on, many years ago, I worked on related phenomena. Instead of measuring absorption edge, we actually measure the diffraction of a photoelectron. And it is related to this exact technique. So that's why I know a lot more about this technique in the technical term, how to analyze and things like this. And most of the time, when you do XAP technique, you do require a high energy physics facility called a cyclotron, and Canada has one. It's called the Canadian Light Source. It's located in Saskatchewan, University of Saskatchewan, and we'll talk a little bit more about that when we get to this. And then other technique that people heard about, I'm sure, scanning tunneling microscopy, which make use of the actual tunneling effects between two atoms, between the atom on the tip of your machine and the surface of your material, and that gives you a current, and you can measure this current and give you topography of the material. So for example, this is a basic STM material. So this is a 7x7 reconstruction material of silicon 111 surface. I'll explain to you how all this notation works, but for now, think of it as just a silicon wafer. And if you clean off your wafer very, very clean, you will see atomic atom, silicon atom that you have here. And then you have this little tip that you mounted here. You can try this drawing trying to show you this tip is atomically sharp. And if you can position this tip very, very close to your silicon atom, tunneling will occur, because the tunneling current go as e to the minus k z, and z is the gap between your surface atom and your tunneling current. So there's an electron decay tunneling probability, if you like, between the gap of this, between the tip atom and your surface atom. And it's extremely, extremely surface sensitive. Why? Because this tunneling current depends exponentially on Z, how far away they are. So if you are too far away, you drop off very quickly. So this gives you atomic resolution. You can actually image the position, the electric position of the surface. But there are problems with this. I'll explain when we get to the STM part. The key about this, right? The key about this technique is based on material science, because people discover piezoelectric material. So this is piezoelectric. This is why I show this plot. Why STM works? It's not that people don't understand tunneling phenomena. They do understand tunneling phenomena for a long time. It's a technical breakthrough, really. It's because people discover how to make piezoelectric material, and therefore they can put the tip on a piezoelectric material. What is piezoelectric material? Piezoelectric material is a material that if you apply a voltage, the material will stretch. Okay, so piezoelectric material is a smart material, right? What they call smart material, because it responds to a stimulus, right? So the stimulus will be my voltage on this piezoelectric material, and then you stretch. You stretch very, very tiny amount of dimension, and this is how you can control, because you crash the tip if you don't have very, very fine control of this of positioning the tip atom as close to it as possible. So when they discover piezoelectric material, the IBM Zurich group discovered how to incorporate it into a tip structure like this. And then all they have to do is to just apply a potential, right, on voltage onto this piezoelectric material. Then you can extend the length of this arm, and therefore position very, very close to this. Okay, so very, very fine control positioning is based on piezoelectric. And of course, they are very smart electrical engineers, because you are detecting very picoamp current, very, very tiny amount of current. So you do need very good electronic as a feedback loop to feedback into the piezoelectric. So two things was STM piezoelectric for positioning your tip, and feedback loop, smart electronic to feedback, so that you can maintain positioning of this scanning of your. And you can find a little bit more about this from this link and so forth. And IBM, of course, is a big contributor to this. The IBM Zurich group, of course, invented these STM technique in 1986. 1986 Nobel Prize to two researchers in IBM. And then subsequently, people do a lot of fancy thing with this technique, and almost now, most of the lab around the world would have STM somewhere on campus, and the IBM has a group in